In a city in Iran, residents absorb a dose of radiation every year that's equivalent to 260 CT scans. They've lived there for centuries, and some studies suggest they might actually be healthier than you are. There's a unit called the millisievert, or MSV. It is used by organizations like the World Health Organization to set the safety limit for how much radiation a person can absorb. The recommended limit for you and me is just 1 MSV per year. That's the line between what's considered acceptable and what's considered dangerous. In Ramsar, a city in northern Iran on the shores of the Caspian Sea, people in certain homes absorb between 70 and 260 MSV per year. In some specific spots, readings have even hit 800 MSV annually. These are numbers that would make any nuclear safety regulator order an immediate evacuation. But nobody evacuated. Nobody left. And when researchers from Tehran University went to study the impact of this exposure, what they found was not what they expected. This is the story of For Places on Earth, where physics says healthy human life should not be possible and where it happens anyway. And by the end of this video, you will understand why this discovery has divided the scientific community for more than 30 years and remains unresolved. First, let's get something straight. Not all radiation is the same, and natural doesn't automatically mean safe or dangerous. You are absorbing radiation right now from the sun, from the ground under your feet, from the food you eat, even from flying in an airplane. We evolved on a radioactive planet, and our bodies have ways to handle moderate amounts of it. The global average for natural background radiation is about 2.4 MSV per year. In high-altitude places like La Paz, Bolivia, that number goes up to around 12 MSV a year, and nobody is treating La Paz like a exclusion zone. What makes Ramsar different is not just the sheer amount of radiation, but where it comes from. The region's hot springs are naturally full of radium-226, a radioactive isotope that comes up from deep within the Earth. For centuries, residents have used materials from these areas to build their homes. The local limestone, soaked in radium, makes up the walls, the floors, and the garden fences. The radiation isn't just in the air or the soil. It's coming from inside the very walls where people sleep. This was documented in detail back in the 1990s by physicist Mohammed Sarabi. He mapped the radiation levels house by house and found it was completely uneven. Some homes had levels close to the global average. Others were like living inside a nuclear power plant without any protective gear. Now, if the standard scientific model is correct, the one that says any amount of radiation increases your cancer risk, Ramsar should be a disaster zone. A population exposed to doses to 100 times above the recommended limit for generations should have skyrocketing cancer rates. But when researchers led by SMJ Mortazavi compared cancer rates in Ramsar to other Iranian cities, they found no statistically significant increase in cancer deaths in the high radiation areas. Even weirder, it looked at the immune cells of Ramsar residents. When they exposed these cells to even more radiation in the lab, the cells from people in high radiation areas showed less damage than cells from people in low radiation areas. It was as if their bodies had developed a built-in defense system, an adaptive response to the constant exposure. This isn't proof of anything on its own. It's a signal that points to a controversial idea called hormesis. But before we get into that, we need to take a trip to Brazil. On the coast of Espírito Santo state lies the city of Guarapari, famous for having some of the most radioactive beaches in the world. The culprit is monazite sand, which is rich in thorium and uranium. On some stretches of beach like Praia de Areia Preta, you could get a dose of up to 175 MSV per year just by spending a lot of time on the sand. Brazil's Nuclear Energy Commission has monitored the area for decades, and their long-term studies found no excess cancer deaths in the local population compared to nearby towns with normal radiation levels. In fact, tourists flock to Guarapari for the supposed therapeutic properties of the sand. The pattern is starting to look familiar, right? High radiation, a resident population, and no documented catastrophe. And it doesn't stop there. In Kerala, India, the monazite beaches expose residents to annual doses of up to 70 MSV, 30 times the recommended limit. One of the largest studies ever done on this topic followed over 385,000 people for decades. The result, published in the journal Health Physics, found no significant link between natural radiation and cancer rates. Then there's Yangjiang, China. The natural radiation there is 3 times higher than the Chinese average. A 40-year study involving over 100,000 residents came to the same conclusion. No detectable increase in cancer mortality risk compared to a low radiation control group. For regions, for countries, for independent studies, and all of them contradict the risk model used by regulatory agencies all over the world. That model is called the Linear No Threshold Model, or LNT. It's the official hypothesis of the ICRP, EPA, and most global regulators. It basically says that any dose of radiation, no matter how tiny, proportionally increases your risk of cancer. There is no safe dose. Every little bit adds to your risk. The LNT model was created in the 50s and 60s, based on data from the survivors of the atomic bombs in Hiroshima and Nagasaki, people exposed to a massive single blast of radiation, extrapolating that data to people exposed to low. Chronic doses over a long time was a precautionary decision, not a scientific certainty. What Ramsar, Guarapari, Kerala, and Yangjiang all suggest is that the human body might respond very differently to chronic, low-level radiation than the LNT model predicts. This brings us back to the idea of hormesis, the theory that low doses of a stressor, like radiation, can actually kick our cellular repair mechanisms into high gear, making them more efficient than they would be otherwise. Your body learns to defend itself better. In 1980, researcher T.D. Lucky published a book compiling hundreds of studies that suggested stimulating effects of low radiation doses. The scientific community was deeply skeptical, not because the data was bad, but because the implications were huge. If the LNT model overestimates risk at low doses, that there are entire global framework for nuclear safety, for evacuation zones around places like Chernobyl and Fukushima, all of it would need to be reevaluated. And that's where the debate stops being purely scientific and becomes political. In 2018, the American Association of Physicists in Medicine stated that the LNT model should be used to estimate health risks for doses below 50 MSV. But the U.S. National Academy of Sciences, in a major report, maintained LNT as the standard. To opposing positions from the same scientific community, the people of Ramsar are living right in the middle of this deadlock. They didn't choose to be part of an experiment. They were just born where the earth runs hot, built homes from the local stone, and lived their lives. Science came to them later, with dosimeters and blood tests, and left with questions it still can't answer. So what does Ramsar really tell us? Not that radiation is safe, not that you should move into a nuclear plant. It tells us something much more uncomfortable, that the models we use to measure risk might be flawed, especially at the low levels where most of us live, where entire regulations are built. Physicist Bernard Cohen spent years challenging the LNT model, showing that U.S. counties with higher natural radon levels actually had less lung cancer, not more. His critics attacked his methods. His defenders pointed out that nobody ever disproved the data itself. Science works slowly, with friction, and politics often gets mixed in. And while it all unfolds, families in Ramsar sleep next to walls of radium-226, wake up, drink their coffee, and take their kids to school. And no study has yet been able to say for sure what that means for their bodies. What we left with is a fundamental question. If the model we use to protect ourselves was built on data from nuclear explosions, is it really the right tool to understand what happens when the Earth just naturally simmers from below? The safety limits that protect you today were built on data from a nuclear bomb dropped in the 1940s. Ramsar has been around for centuries. If that changes how you think about risk or changes nothing at all, let me know in the comments. This is one conversation that still has no right answer. Thanks for watching.